All right. Hello and welcome back. It's been a while. I know you missed me. I certainly missed you. I've been bombarding you with homeworks and projects. Um, and there will be a few more, but remember, this is a graduate class. And so, yeah, you have to figure out how to manage your time and fill in the gaps you have. And trust me, this in the future, you're going to be like, yeah, I'm glad we did this. If I tell you about my CFD class, I wish I had this class compared to my CFD class. So I was doing unstructured grids in my CFD class, and so you guys are just dealing with structure, and we had to write code in C, okay, for unstructured grids, and so this is a little bit more convenient. I don't think it's necessary to go unstructured because you don't learn. The purpose is to learn the phenomena and then figure out. If you learn the basics, you can figure things out on your own later. Which isn't the point I was just trying to make. The last few lectures in this class, and my intention for your final projects are to be just surveys about CFD topics. Because once you know the guts of how to rip a partial differential equation apart, put it on a grid, understand the basic stability, convergence, and error analysis, you can apply these concepts to any new situation you're dealing with. And so that was the purpose of the parallel computing lectures, just to tell you what's out there. And I hope it was helpful. It's certainly a big specialty. You can spend your lifetime doing parallel computing. Tim, would you mind putting half-lights? Half-lights. It's written. There's half-lights written on it. Okay, and then there's lower. Yeah, press it. Keep pressing it. Okay, I think this is okay. You guys can see, right? Okay, so today's lecture, we are done with core CFD and incompressible flows. So in a way, the hardest part is kind of over, where you wrote a CFD code. And now we're going to dig a little bit deeper into why we observe what we observe sometimes when we run simulations. So in your career, you're going to see that if you use CFD, you're going to run a simulation. At some point, you're going to see some wiggles in the solution. And we saw some of those early on in the class when we did the advection diffusion equation with central and upwinding. And we kind of partially understood that. For the next few lectures, we're going to dig really deep and understand why these things happen. You're going to see if you're transporting a pollutant using different types of schemes, you're going to see it diffuse or maybe start doing wiggles, and we're going to understand where these come from. So I call this lecture Numerical Phenomena. It's really tied into physical phenomena, which is interesting. The numerics are going to produce physical phenomena that we understand. So the idea is that it's possible to explain the behavior of in numerical methods the numerical solution of these linear PDEs we saw earlier. And the procedure it consists of decomposing a complex signal into its separate frequencies. And in other words, that's called spectral analysis. And the great thing about spectral analysis is that it takes away the space component and makes it into a spectral component where you look at a full signal as a linear summation of frequencies, sine waves and cosine waves, or the combination exponentials, essentially. So what we're going to do now, we're going to experiment with the following signal. U equals sine 2 pi x plus sine 4 pi x plus sine 6 pi x. And this is plotted over here. The full solution is this blue guy with the stars. And the signals, the individual wave components that compose this signal are shown here. So you see the lowest frequency in green, which is sine 2 pi. And then the sine 4 pi, that's the one in red. And the sine 6 pi, it's the one in magenta or blue, light blue. Okay? If you add these up, you're going to get that total signal. Okay? Right? Now, I'm going to take this and consider it as an initial condition, take it as an initial condition, and I'm going to subject that initial condition, that initial signal, okay, shown in blue again, to a partial differential equation of this form. It's linear because with linearity we're going to be able to explain a lot of things. Nonlinearity just complicates things a little bit, but you'll see that the phenomena are not that far away from what happens in a linear differential equation. So you have a first derivative in time, and then a bunch of coefficients multiplying the first derivative, second derivative, third derivative, fourth derivative, and so on. We haven't seen these types of derivatives in computational fluid dynamics, but they actually do arise from the numerical solution, okay? And we'll understand how. And actually, in solid mechanics, you can reach third and fourth derivatives when you're doing some solid mechanics analysis. Okay, so now, this is my initial signal subject to three different PDEs, okay? And obviously, this signal is behaving differently under these three situations. Can you tell me what these three situations are? So let's start with the first one. You take the initial signal, and the whole thing is moving in one direction. What is that called? Convection, advection, okay? What about the second one? Diffusion. What about the third one? What the hell is going on? If you've seen this before, probably in Professor Sutherland's graduate numerical methods, but if you haven't seen this, do you know what this is? Okay, so this is called dispersion. When you subject this initial signal to a first derivative on the right-hand side in space, you get advection. When you subject it to a second derivative, you're going to get diffusion. But then what happens with the third derivative, you get this weird thing going on. Now we're going to try to understand why this happens. How can you take this signal and just make it behave all sorts of wiggly, strange ways? Okay. And so this is where we bring in Dr. Elizabeth. This is a cartoon from XKCD. If you know the website, it's this physicist guy who does cartoons about science and funny stuff. So anyway, what we're going to do now, we're going to take this signal and the PDE, the linear PDE, and apply a Fourier series, do a Fourier analysis on that signal, and substitute the Fourier analysis into the PDE, and look at how the individual frequencies, the sine 2 pi, sine 4 pi, sine 6 pi, how they behave when we subject them to advection, diffusion, and dispersion. Okay, and you know, if you don't remember your Fourier series, this is just a basic summary. In 2D, we can write any signal as a summation over frequencies from -infinity to infinity of some coefficient times a complex exponential in time, complex exponential in space, and the wave number, you can call this k as the wave number, or m, the wave number, is just 2m pi over L, the space domain. And then if you call u hat k the coefficient e to the a, then you get this nice compact form, e to the qt, e to the ikx. But q can be a complex number, okay? So don't worry about it. We don't worry about how this came about. We can show you how to do this in Python, but this is correct, okay? And if you don't remember your Fourier analysis, just go jump on Wikipedia or just Google Fourier series, and you'll see how it's done. So this is equivalent to the sine and cosine series. You've probably seen the sine and cosine series. Remember the Euler identity, e to the I theta equal cosine theta plus I sine theta over 2. Okay, so it's the same thing, but that's why you get from -infinity to +infinity. Anyway, we're going to be dealing with this form. Now, our signal, our u of xt, looks like this. We're going to assume it has this form. Okay, so we're going to take this signal and we're going to substitute it into the linear PDE. But because we are linear, we can only take one individual frequency. So let me just set some nomenclature. We're going to call from now on, we're going to call k the wave number or the frequency. Okay, so the higher the k, the higher the frequency. Okay, so in the first case we had 3 k's, 2 pi, 4 pi, and 6 pi. Okay, and then you can deduce m from those numbers and L, etc. Okay, but k is the wave number or the frequency. All right. So because the differential equation is linear, we can just deal with one wave mode, one wave number. Okay, so we don't have to carry the summation all along. Is this clear? So if you substitute the summation of the PDE, what's true for one wave number is going to be true for the entire summation because it's linear. Okay. So to simplify things, we're just going to assume u is equal e to the qt e to the ikx, or you can call uk is e to the qt e to the ikx. So let's just get some derivatives out of the way. Du by dt, if you differentiate this with respect to time, it's qe qt e to the ikx. So du by dt is qu. Okay. And what about ux? Take first derivative in space, ik comes out, and this whole thing stays the same. You get iku. That's what's so great about using the exponential Fourier series rather than the sine and cosine. Okay. Then you take one more derivative. So ux is iku, uxx is I squared k squared u, right? You just differentiate one more time. You differentiate one more time, you get I cubed k cubed u. And then for the nth derivative is simply I to the power n, k to the power n u. Okay? So now let's see what happens with the advection equation, with the advection process. Advection is defined with u sub t equal minus cux. So du dt is minus c du dx. Now what we're going to do, we're going to take uxt, the one component, e to the qt e to the ikx. Okay. If you feel the math is too much, just let me know. I can write it on the board. So I'm trying to spell it out, but I don't want to bore you with the math. So just let me know if you want me to go slower or faster. Okay. So we substitute the derivatives. Remember, ut is qu, and ux is iku, and you multiply by c. So you get qu is equal minus ICKU. Okay. In other words, Q is minus ICK. Now, why are we after Q? Because we know what K is from the initial condition. If you look at this decomposition, uxt equal e to the qt e to the ikx, all terms that have an imaginary number, an I in them, they represent space. And that can be obtained from the initial condition. At t equals 0, this term is 1. So for the initial condition, we can obtain q. So k, sorry. So we know what k is from the initial condition. What we're after is q. And q is going to be determined from the PDE, the relation between du dt and du dx, or d2u by dx squared. Okay, so that's why we're looking for q over here. We know because we know k. Okay, so for the advection equation, q is actually just an imaginary number. It's minus ick. So when you plug it back into the governing equation, into the total solution, you get summation e to the minus ikct e to the minus e to the ikx, and you combine exponentials and you get e to the ikx minus ct. Now, what does this remind you of, x minus ct? It reminds you of the exact solution of the advection equation. It's an initial condition, okay, translated by minus ct, okay, and it shows up in this term here, okay? Okay. Now, what's important to note is if you agree that x minus ct is just going to move things as time increases, we're going to move the signal, we are moving all frequencies k by the same speed, okay? Because they're all multiplied by this term. There's no, all k's move at the same c. There's no scaling in c. This c is the true c that showed up in the governing equation, okay? So all frequencies move at the same speed c, and advection always results in q equal minus ick. So let me show you. So what I did here is actually take the exact solution of the advection equation, and then I did the Fourier transform and plotted the individual frequencies. So look what happens. The total solution moves, and each frequency moves at the same speed. They all move at the same speed. That's what advection does. It makes sense, right? For this to move, to retain its shape and move in one of the directions, all of its frequencies have to move at the same rate. Okay? Okay. This is interesting. So now let's look at what happens with diffusion. So diffusion is du dt is mu d to u dx squared. Again, we're going to assume u equal e to the qt e to the ikx. We substitute, we get qu for ut, remember our derivatives, and uxx is I squared k squared u multiplied by mu. Okay? Then I squared is -1, so that gives us q equal minus mu k squared. It's real. Now q is a real number. It's not an imaginary number. Okay, now we said imaginary numbers are going to impact space, but real numbers, what are they going to do? They're going to impact time, how things change in time. Okay? So now we compose the total solution. You get e to the minus mu k squared t times e to the ikx. So this term is going to modulate. This term is like an amplitude now. If e to the ikx gives you a signal in space, only has space in it, e to the minus mu k squared t is going to change the amplitude of that signal. Okay? So now what can you observe in this? First of all, the diffusion acts on all the frequencies. So we're going to diffuse all frequencies. But what other observation can you make? So if k is equal 2 pi and k is equal 4 pi, which one is going to diffuse faster? Excuse me? Why? Yeah, you have k squared. So the larger the k, or the higher the frequency, okay, the faster this is going to diffuse. So again, think of this. This is a linear combination. It has e to the minus mu 2 pi squared t e to the I 2 pi x plus e to the minus mu 4 pi squared t, okay, e to the I times 4 pi x, and so on. Now, each one of those terms over time is going to shrink, but at a different rate. And that rate is proportional to the frequency. Okay? So this is very important because it tells us now that higher frequencies are going to dissipate faster than lower frequencies. And this is a pretty powerful statement. One more thing, though, is that if mu is negative, so that explains why the diffusion, what happens when you have reverse dissipation. If mu is a negative quantity, this exponent here becomes a positive quantity, and it's just going to grow in amplitude over time. So you get instability. So that's why negative diffusion doesn't make sense. Just from the math, not from the physics, just from the math, negative diffusion doesn't make sense. Okay, so let's see what happens now. This is our signal. First, look at the plot above, and then look at the plot of the individual frequencies, okay? See what happens? This interesting shape, it's not moving in space because we're only modifying the amplitude with diffusion, okay? So it retains its stationary in space, but changes over time, okay? But look what happens. The highest frequency dissipates the fastest, then the 4 pi, and then the 2 pi at the end. So the 2 pi frequency is going to take a long time for it to finally diffuse. So how can you use diffusion then? As a filter. So what if you have a noisy signal like this? How can you filter it? This is an image processing. Or you're just taking a signal that's very noisy. What do you do with it? Subject it to diffusion. See what happens? Right? Look at how we killed the high frequencies almost instantly. These high frequencies are like 100 pi. Okay, when I built this signal artificially, I superimposed like a very high frequency on top of it. And it's shown here in the Fourier series. Look at it. It's just like dissipates instantly. So this is actually called a filter in computational fluid dynamics. There is something called the filter operation that we use when we're doing compressible flows sometimes. We have to filter the pressure. We have to filter noise on the pressure. So we subject it to a fourth derivative. Okay? So if diffusion with the second derivative acts at k squared, diffusion with the fourth derivative is going to be k to the fourth. So it's going to dissipate even faster. Okay? All right. So now to the elephant in the room, third derivative, or dispersion. Okay? We said this is going to look like ut equal d for dispersion, uxxx, third derivative. Again, we'll subject it to e to the qt, e to the ikx. And when you apply the differentiation, you get ut is qu, and uxxx is I. You remember, the nth derivative is I to the n, k to the n, u. So this is I cubed, k cubed, u times d, the dispersion coefficient. Now, pay attention what's going to happen here, okay? Because dispersion is actually very similar to advection, or advection is dispersion of the first order, in other words. But let's see what happens. Q is minus I dk cubed. So that tells us that dispersion is going to act on space. It's not going to change the amplitude over time, but it's going to immediately act on how the signal looks and changes in space, because it's imaginary, okay? So we substitute it back into here. Okay, so let me move to the next slide. So what you get is your total solution is e to the ik x minus dk squared t. Now compare this to advection. Advection, we had x minus ct, and that c was constant, okay, for all frequencies. But with dispersion, what happens? It depends. Your speed is going to depend on the frequency. So the higher the frequency, the faster it's going to move. Can you see it now? We made the signal move as a function of its frequencies, of its individual frequencies. That's what's so cool about dispersion. So different waves move at different speeds, and waves of frequency k move at speed dk squared. So therefore, higher frequencies travel faster than lower frequencies. Dispersion does not cause instability, but it can rip a signal apart. So, okay, let's see how this works. So first look at the above plot, and then look at the bottom. It's really cool. How the heck can you get this? Well, this is how you get it. The higher frequency is going to move faster. That's the 6 pi is going to move faster than 4 pi, is going to move faster than 2 pi. And that's how you rip a signal apart, okay? Okay, so what does dispersion tell us then? What if you had a signal that had a lot of frequencies? If you have a sine signal, one sine, like sine 2 pi, that has one frequency. You know, it doesn't matter, it's going to move. If you subject it to dispersion, well, it's a signal frequency. You're not going to see it being ripped apart because it's just one sine wave. But what if you had a signal that had thousands of frequencies? So what's a signal that could have thousands of frequencies? Like a step function or a Gaussian or any complex function that has a sharp interface, or that has a weird look and shape. Okay, so a step function or a square function. So let me show you. This is an example of a step function from -1 to 1. If you take the Fourier series of this, you're going to end up with like hundreds of thousands of frequencies. So what's going to happen when you subject this to dispersion? What do you think is going to happen? The highest frequencies are going to move fastest, so it's going to rip it apart. It's stable from a numerical perspective, but you get all of these wiggles. Okay? So now, I want you to think in the opposite direction. If you see something like this, you're going to immediately conclude, you should immediately conclude, well, I probably have some dispersion present in my numerical method. Okay? When you see a signal diffusing, you should immediately say, well, I probably have some diffusion in my numerical method. And when you see your signal moving, it's going to have advection, but that's kind of the trivial case, okay? Those, diffusion and dispersion, are the two key phenomena that you will observe in numerical methods. Okay? Now we just need one more step to understand why they show up in numerical methods. So I have a summary slide here for advection, diffusion, and dispersion. But we don't have to stop here. Okay? We can define advection, dispersion, and diffusion to any order. So what we conclude from this really is that odd derivatives, 1, 3, 5, 7, all odd derivatives mean advection and dispersion. Okay? Only the first derivative means advection. The higher odd derivatives, third, fifth, seventh, etc., they mean dispersion. And the higher the dispersion derivative, the faster these signals are going to move. Okay? So if you had a fifth derivative, you're going to move them at decay to the fourth. If you had a seventh derivative, you're going to move them at decay to the sixth. Same thing with diffusion. All even derivatives, okay? You can do the analysis e to the qt. You can show in general that q is going to be a real number for diffusion and q is going to be a complex number for dispersion. The higher the diffusion order, the faster you're going to dissipate high frequencies. Okay? And this slide is just for completion. It shows you what q, the value of q, is for a general diffusion term and a general advection term. Okay? Now in practice, we're rarely, at least in transport phenomena, we're never solving an equation that has a derivative higher than 2. But I'm going to show you that high order derivatives actually show up from a numerical method. Okay? And that's what causes weird behavior that you see in numerical simulations. Okay? So odd derivatives cause dispersion, even derivatives cause diffusion. So how can we use this to analyze finite difference schemes? I'm going to be focused on finite difference schemes because they're easier to analyze than finite volume schemes. But the ideas are all the same. You see this in finite volume methods. You should immediately be able to say, yeah, this is dispersion over here. You know, how do you get rid of dispersion, for example? You add a little bit more diffusion. Okay? So there's no way, if you're stuck with dispersion, then you can artificially dissipate those frequencies that come out. Remember, the highest frequencies are going to come out first. You can dissipate those by adding diffusion. Okay? And we'll see more of this in the next few lectures. Okay, so to show you how we can use this to analyze FD schemes. So now I've just introduced you to these three phenomena: advection, diffusion, and dispersion. Okay? Keep those in mind. Now we're going to get back to numerical methods and see how they show up. Okay? So let's take the forward in time, central in space advection. Okay, we are all familiar with this, phi n plus 1 minus phi n over delta t in central in space. And we know this scheme is unconditionally unstable. So if you run it with the same initial signal that we were dealing with, it's just going to blow up. Okay? And now if you go upwind with a CFL, let's say 0.5, you're going to advect that solution. But what's happening to it? It is dissipating. Okay, so from what we learned, it seems that we are not actually solving this equation. We're solving that equation plus a diffusion term. So where the heck did that diffusion term come from? Okay? Are you guys following me so far? You agree that we're actually, if we were solving the diffusion equation, if we were solving, the advection equation, that signal will just move. But we see it diffuse. So this means we have somehow artificially added a diffusion term. So where did this come from? It actually came from the truncation error. Okay? So this is a little animation I did for a seminar I gave once. So what we're going to do now, we're going to look at the truncation error and see, so what's the difference between the exact solution and the numerical solution? This is truncation error. And we noticed that the numerical solution showed us some diffusion. So it must be, the only logical conclusion is that the truncation error somehow snuck back into the numerical method and added diffusion somehow. Okay? So we're going to show this. All right? So it turns out that a numerical scheme, such as the central scheme, does not actually solve this equation, d phi dt plus c d phi dx, it actually solves an equation of the form we started with, a general linear differential equation. Okay? It has first order advection, second order diffusion, third order dispersion, fourth order diffusion, and so on. Okay? And I'll prove this to you in a minute. Okay? Odd derivatives, remember, odd derivatives cause advection, dispersion, and even derivatives cause diffusion. Now, this equation is called the modified equation. Okay? So when you take a finite difference scheme and you recognize it actually does not solve the equation we set out to solve. It solves another equation that has this form for linear PDEs. Okay? This equation is called the modified equation. It is the true equation, or it is the equation that the numerical method is actually solving. Okay? And let's see how we derive it. Let's take as an example the forward in time, upwind in space, the upwind scheme. So ut plus cux equal to 0. And then we're going to use an upwind scheme for this. N plus 1 minus n, then ui minus ui minus 1. Right? We're assuming c is positive. Okay? Let's do it. So what I'm going to do now is going to try to recover a continuous PDE from this scheme. Okay? So what I'm going to do, I'm going to take uin plus 1 and expand it around uin. And I'm going to take ui minus 1n and expand it around uim. Okay, just two Taylor series. We know how to do those. So uin plus 1 in time, that's uin plus utn at I plus delta t squared over 2 u double prime at I, and et cetera, et cetera. Okay? Classic Taylor series around n plus 1. And then the other Taylor series for ui minus 1. Now we're dropping cross derivatives term because they don't really matter in this case. ui minus 1n is uin plus delta x, the first derivative with respect to x, and then second derivative with respect to x, and so on. Okay? So I'm trying to turn the discrete terms into continuous terms. These are continuous terms, right? They look like a differential equation. So what I'm going to do, we'll take these two guys and substitute them back here. We're going to take this guy and put it up here. We'll take that guy and put it up here. And everything else is going to be in terms of uim, okay, and its derivatives. Okay? So when you do this, it's really tedious algebra, but you know we've all done it. You may have to do it in your homework. You go substitute, you get this nasty expression that has first derivative in time, second derivative in time, third derivative in time, and a bunch of derivatives in space. Okay? Now, the first thing to notice is that we actually recover our differential equation that we set out to solve, right? And this is actually the truncation error. This whole thing is the truncation error, because this is not 0. It is 0 in the limit of delta t and delta x approaching 0, but there's a finite error. Okay? So this is the equation we set out to solve, but it's not equal to 0. So obviously this truncation error is causing this diffusion and dispersion. But we have a problem on the right-hand side. I want to express all the time terms as in terms of space. Okay? So that I have u sub t equal a bunch of spatial terms. Okay? A bunch of spatial derivatives. Okay? So let's do that. How can we do this? We're going to take our original partial differential equation and differentiate it with respect to time. Okay? So if you take the time derivative of this PDE, then you get second time derivative here, and then utx. But we know that u sub t is minus cux. Okay? So you get utt minus c squared uxx equals 0, which means the second derivative in time is c squared uxx. And you do the same for utt and utttt, etc. And you keep substituting and collecting terms together, and so on. And then when you do this, this is what you get. This is the equation that we set out to solve, but it's not 0. It has an error term that looks like first error term is a diffusion term. And now that explains why we get diffusion from the upwind scheme. Because the upwind scheme is solving this equation, not ut plus cux equals 0. It's solving ut plus cux equals some diffusion term, plus some dispersion term, plus some higher order diffusion. But you know what? These terms are insignificant compared to this guy. Okay? Makes sense now? And you can do this same procedure for the central scheme. And for the central scheme, you can show that this term is negative, which is the diffusion coefficient. And that's why the central scheme is unstable. We did this in the first few lectures in class. Okay? So in other words, the modified equation actually informs us about the processes that actually are introduced by the numerical method. You can think of it different ways. The numerical method is not solving the equation we set out to solve. It's solving a modified equation. And that modified equation has diffusion and dispersion terms in it. Now, depending on the strength of these terms, you know, you're going to get interesting and strange behaviors. Okay? I'd rather have diffusion over dispersion every time, every day, because diffusion actually has a tendency to stabilize things, to reduce overshoots, right, over a sharp signal. Dispersion can rip a signal apart. So I'd rather have my leading order term be a diffusion term, always. Okay? All right, so let's look at the modified equation for a few schemes. For the forward in time central in space, phi t equals c phi x, you do it, you do the modified equation analysis, you get a negative, delta t is positive, c squared is positive, and minus this guy is actually a negative term. So you get a negative diffusion coefficient, and we showed from our Fourier analysis that negative diffusion, reverse dissipation, is unstable, is going to cause unbounded growth. Okay. For the upwind scheme, this is what you get. We just showed this equation. Should have, there's a negative sign in here, but anyway, this is the idea. But this is only stable as long as c delta t over delta x is less than 1. Okay. And it just so happens, Aaron asked this question like 2 months ago, that all the other terms have the same form. They're 1 minus CFL, the Courant number is called the Courant number, to a certain power. So c dt by dx less than 1 guarantees that this scheme is stable. Okay? But it is diffusive. What happens if you set it equal to 1? It's you get an exact solution. It is the only equation and the only scheme, and it only happens in 1D, that if you use upwind with a Courant number of 1, you're going to get an exact solution. That's like one heck of a unique case. Okay? All right. So it's called the numerical dissipation. Now, this is the Lax-Wendroff scheme. Okay? It's an interesting scheme, and what it does, it's a central scheme, okay, and it's trying to combat the negative dissipation that was introduced by the central scheme. So if you go back to the central scheme, you would say, okay, how can I get rid of this term? Maybe we can add a c squared delta t over delta x, whatever, second derivative over here. So let's add a diffusion term to the central scheme to get rid of this term. If you do that, you get the Lax-Wendroff scheme. Okay? So the Lax-Wendroff scheme, Lax-Wendroff has an additional term that is actually a second order approximation to the diffusion term in the central scheme. So this guy is going to kill the negative diffusion from the central scheme. And you apply it to this beautiful solution, see what happens. Yeah, there is a phase shift compared to the exact solution. You cannot see it here because I'm not plotting it on top of the exact solution, because there's still a dispersion term. So let's look at the modified equation for the Lax-Wendroff. The leading order error in the modified equation, see how we got rid of the diffusion term. There's no diffusion, but there's a dispersion term. Okay? And if you run at Courant number of 1, So you're going to get an exact solution. But if not, what happens to a sharp signal with the Lax-Wendroff scheme? You're going to get a nasty dispersive solution, okay? Lax-Wendroff. I'd rather have diffusion than dispersion, okay? Because this is causing overshoots, okay? So the Lax-Wendroff scheme tries to combat the negative dissipation of the central scheme, okay? But you end up with a dispersion leading order error, okay? The coefficient. Yeah, so you can probably, or you can add a dispersion term, so you only get higher order diffusion. Okay. Just a few other modified equations for completion. Backward in time, central in space. We know that this is unconditionally stable. Okay, you can show that this diffusion term is positive and all the other diffusion terms are positive. Now, you're starting to see a pattern here, right? If the diffusion coefficients are positive or negative, I don't know, the higher order diffusion terms, they need to satisfy a certain sign to make sure that you're going to be stable. Because dispersion is not going to cause instability. It's just going to cause weird wiggles that are just going to move. Okay, they're going to keep moving. But it's the diffusion terms, the even order derivatives that can destroy your solution, make it unstable. Okay, Lax-Friedrichs, it's another scheme, classic scheme used for the advection equation. It is very diffusive. Okay, diffusion coefficient. Okay, so now I want to relate this to the amplification factor and stability. We saw that from the modified equation, you can argue and reason about why a scheme can be unstable. Central scheme had negative diffusion, therefore it was unstable. But then what about the higher order diffusion terms? Turns out that there's actually a relation between the stability of a differential equation of a numerical scheme and the modified equation. Okay, there's a relation. And if you remember, the von Neumann stability analysis is actually the same thing we're doing. With the von Neumann stability analysis, we took a differential equation of this form. Now we're going to generalize it. We're going to apply the von Neumann stability analysis to our modified equation. Okay, but I'm going to separate now the advection terms and give them coefficients C. I should have chosen D for dispersion, but let's say C for convection. C1 ux, C3 uxx, and so on. And for all the diffusion terms, mu2 uxx, mu4 uxxx, x, okay, and so on. And we just write this in this general form. For the dispersion terms, summation for over C2n plus 1, because this is an odd derivative, and the odd derivative of u with respect to x is to n plus 1, starting from n equals 0. So you get C1, C3, C5, C7, and then first, third, fifth, seventh, etc. derivative, okay? And then for the diffusion terms, you get, for n equal 1, you get the first diffusion term, and so on and so forth, okay? Now, the von Neumann stability analysis was essentially just the same thing we did, was applying the Fourier series, okay, to a differential, to a numerical scheme. But now I'm going to try to tie in the amplification factor from the von Neumann analysis to the coefficients of the modified equation. Okay, and you'll understand the reasoning behind this in a second. Okay, so we will take this same form for a given wave, for a given frequency k. We're going to substitute it up there. We know what these look like. We just did them earlier. So ut was qu, and then for the dispersion terms, we have c to n plus 1, and this derivative is I to the 2n plus 1, k to the 2n plus 1 u. And for the diffusion terms, you had I to the 2n, k to the 2n u. Okay? So clear so far? Okay? So again, okay, so let me remind you, though, that the amplification factor is this term. Okay? Or the real part of this term, because that is going to tell you if your solution is going to grow over time or going to dissipate or stay the same. Okay? So we're after Q, in other words. all right? So if QU is this expression, then Q is that expression. And now you notice that I to the 2n is actually a real number. So this whole thing is a real quantity because diffusion is going to result with a real exponent, right? So it all makes sense now. It's just going to change things in time. And dispersion is going to result, so I to the 2n plus 1, that's I times I to the 2n. So this is an imaginary number, okay? Imaginary portion of the number. So in general, you can write Q as a real number plus just a real component and an imaginary component, A plus IB. Okay, so what is A? A is this whole thing, the diffusion guy, and B is this whole thing except an I. And notice that I to the 2n is minus 1 to the n. Okay? Okay, for n equal 1, you have I squared, that's minus 1. For n equal 4, for n equal 2, you have I to the 4th, okay, and so on and so forth. All right? Okay, great. So now we have A plus IB. This is what we have for A plus IB. And A is this guy, B is that guy, okay, the diffusion component, and the imaginary component of the exponent. Okay, and remember, e to the qt is the amplification factor. Now, if you split q into A plus IB, then you can take IB and put it with the advection portion of the signal, and you're only left with this real part. This term is going to tell you if you're going to grow or shrink. Okay, so how can we guarantee that e to the at is going to remain bounded if a is less than or equal to 0? So exponential, if the exponent is less than or equal to 0, then it's either going to remain the same or decay in time. And now if you look at A, is this summation of mu 2n minus 1 to the n k squared. This guy is always positive because it's k squared. Okay? So the only condition we have is that for each n, we need to make sure that the diffusion coefficients minus 1 to the n mu 2n are less than or equal to 0. Okay, so now it all ties back into the meaning of diffusion. Okay? So then what does this mean in practice? It means that the first diffusion coefficient that multiplies the second derivative needs to be positive. But the diffusion coefficient that multiplies the fourth derivative needs to be negative. And you alternate. And then mu 6 needs to be positive, mu 8 needs to be negative, and so on and so forth. Okay? So now if you have your modified equation, if you really have the full expression, you just check, you only have to check the diffusion coefficients, okay, and make sure that they satisfy these signs, all right? And oftentimes, if your scheme, well, all the time, if your scheme is consistent, so essentially the error approaches 0 as you shrink delta t and delta x separately to 0, there's going to be a pattern, okay? Just like the CFL condition, if C delta t by delta x less than 1, we make sure all the diffusion coefficients are, all the mu's are in the correct sign, because there's going to be a pattern, you're going to have a pattern, okay? Okay, so now we tied in stability, this notion of stability, to the coefficients of the modified equation, okay, or the amplification factor, Q, to the coefficients. But still, it's really annoying to derive the modified equation. I mean, it's one thing to talk about the amplification factor. You're like, yeah, the amplification factor is greater than 1 or less than 1. You cannot put your finger on the amplification factor, right? But as engineers, when you look at the differential equation, you're like, aha, there's negative diffusion here. It doesn't make sense. It's unphysical. That's what you want to look at. So I really like to see the modified equation rather than just the amplification factor. Okay, I want to see the modified equation. I want to see the physics that have been introduced by the numerical method. So that means we are interested in the modified equation. But it's really annoying to get modified equations. I mean, we tried it for a simple scheme here, advection. And if you try it for the Lax-Friedrich scheme or some other nasty scheme, it is really annoying doing all these substitutions and derivatives. If you want to get 2 or 3 terms, it gets really complicated. Okay? It turns out that there's actually a way to get these coefficients, okay, if you only know the amplification factor. So that ties us back to the stupid amplification factor, but still, you know, when I want to present stability results, I'd like to present the modified equation rather than the amplification factor. But you have to first agree that it's easy to actually obtain the amplification factor. It's easier, much easier, to obtain the amplification factor than to obtain the modified equation. So what if we know the amplification factor? Is there a way to tie the coefficients of the modified equation to the amplification factor? Yes, there is, and we just actually showed it, but I'm going to formalize it to you. And this is actually the subject of a paper that Moqbil and I and Dr. Sutherland we submitted, and it's still under review. It's been over 3 months, so we're hoping it's going to get accepted. But this is material that's actually being published now. All right. So I'm going to rewrite the modified equation, get rid of the C's and of the D's and the mu's. I'm just going to write it A1ux plus A2uxx plus A3uxxx, etc. And I'm showing the coefficients here in red because we're after those coefficients. And what I want to do now is get the amplification factor, because I said it's easy to get the amplification factor. And then from the amplification factor, get A1, A2, A3, A4. Okay? So let me show you how we can do this. All right? So again, I'm going to take u, e to the q, t, e to the ikx. And in von Neumann's theory and stability analysis, we said that this is the amplification factor. Okay? So I'm going to substitute this, and we're doing this over and over again. Okay? It's just amazing how many different ways you can look at this. Okay? So qu on the left-hand side is simply an, that's the coefficient, I to the n, that's the nth derivative, right? I to the n, k to the nu. So q is simply summation of an, I to the n, kn. So now we know that the amplification factor is related to the coefficients of the modified equation. That's the relationship. Okay? That's the relation. All right? But still, we're going to have to untangle it a little bit. Okay? So in other words, q is I a1k plus I squared a2k squared plus I cubed a3k cubed, and so on. So now how can I, if I know q, how can I get a1, a2, a3, and so on? We have just one equation, right? You just have one equation with an infinite number of unknowns, a1, a2, a3. So what do you do? What do you suggest we do? This is a polynomial, okay? And you're trying to find the coefficients of the polynomial. What do we do? Okay. What if we take the derivative of q with respect to k? Will give us I a1 plus 2I squared a2k, right? Plus 3, etc., etc. Okay? Okay, awesome. What do we do next? What if we set k equals 0? What happens? You get a1. So that gives you a1. Take the derivative of q. If you know what q is, it's not going to be in this form, okay? It's not going to be in this form. Q is going to be some bunch of exponentials and logarithms. But we know that this is the equivalent of q. So we're going to use, we know q, we're going to take its derivative to k with respect to k, set k equal to 0. First derivative is going to give us a1. So how can we get to a2? Take the second derivative. All right. So second derivative with respect to q, this guy is 0. This guy gives us 2I squared a2, and these guys have k's in them. So now what do? Set k equal to 0. And that gives us a2. Okay? Now remember, we know q. Q is some complex expression, logs and delta t's and exponentials. But we don't care about that because we know how to differentiate it. All we have to do is differentiate it, set k equal to 0, and that is going to give us the corresponding coefficients. So how do we get a3? Third derivative, set k equal to 0, that gives us a3. So now in general,
you can generalize this, and the nth derivative of q, the amplification exponent or amplification factor with respect to k, at k equals 0 is going to give you a n, the nth coefficient of the modified equation. Okay? In other words, a n is simply 1 over I to the n times n factorial times the nth derivative of q at k equals 0. So now if you know q, all you have to do is know q somehow. I'm going to show you it's easy actually to know q. If you know q, all you have to do is differentiate it to get the coefficients of the modified equation. That is pretty cool. Okay? Okay, so let's see how, I'll give you an example. Forward in time, upwind in space. So that's the upwind scheme for the advection equation. Okay, we're assuming c is positive, so we're upwinding from left to right. Okay, and this is the finite difference scheme. So how do we get the amplification factor? We do the von Neumann analysis. We substitute u equal e to the qt e to the ikx. Now remember what we did. We used the modified equation to kind of reverse engineer things, right? But we're actually going to apply the Fourier analysis now on the finite difference scheme and get q from the finite difference scheme. Okay, so when you do this, un plus 1 is really at qt plus delta t, right? And un is at qt, and ui is kx, and ui minus 1 is kx minus delta x. So you just substitute this guy over here. Then you divide by e to the qt, okay? And you get e to the q delta t equal 1 minus this kind of expression. We are after q, okay? So how do you get q? You just simply take the logarithm, and this is q. 1 over delta t log 1 minus c delta t delta x. It's easy to obtain q. It's not that hard, okay? So now that we have q, all we have to do is differentiate it to get the coefficients of the modified equation. So the modified equation is this guy, a1, etc. Okay? And we said that a1 is this is not c1, it's a1 is 1 over I times the first derivative of q at k equals 0. Now, this getting the derivative for this is annoying. So let me show you how I do it on my laptop. I use Mathematica. Okay. Where's Mathematica? Let's see. Okay, so I'm going to say q is equal to, what was q? 1 over delta t. So we had q is, oops. And you can do this in SymPy, okay, or Sage, any math stuff. 1 over dt, okay, times log of 1 minus c times dt over dx, okay, into 1 minus exponential, I need I, so you cannot just write I, you have to pick a special I, e to the minus I k dx. Okay, I don't care about dt and dx, right, and dt and dx. What we care about is k, because we're going to differentiate with respect to k. So that gives us q. We said that a1 is 1 over I, correct, dq with respect to k at k equals 0. So this is a Mathematica little trick. We get a1 is minus c. Okay. Then what about the a2 term? a2 was 1 over 2i squared. Where's I? I times I. And you're going to automate this. We have it automated in another code. And then we'll do dq with respect to k, second derivative, okay, at k equals 0. Ta-da. Now you simplify this expression, you're going to get the upwind and the CFL condition. So if I do full simplify, okay, then you can take dx out, and you get 1 minus c dt over dx. And that gives you the CFL condition in Mathematica. Yeah, I mean, you can, once you have the form, you can just simplify it by hand. But yeah, doing these derivatives, because the hardest part of this is that these derivatives are annoying. So let me show you what the derivative looks like. It's really annoying, okay? So you need a symbolic package to do it. But guess what? This is easier to do than doing repeated differentiations. If you want to automate the modified equation analysis using the traditional approach, it's extremely annoying to do because you have to substitute the governing equation. And how do you express the governing equation? It can get really annoying even if you want to program it. So programming this is easier. All you have to do is find the amplification factor, okay? And from the amplification factor, you can get the coefficient of the modified equation. Let me show you another piece of code that we had. Let's see. Okay. It's called Moira. So that's modified equation generator, whatever name was. I used Mike's acronym, silly acronym generator. Anyway, so what this allows me to do is define a left-hand side for the time derivative. So if you see, this is uin plus 1 minus uin over delta t. This is just some mathematical lingo. And then on the right-hand side, I have a bunch of schemes. But over here, I'm just defining the upwind. For example, that's u c over minus c over delta x, ui minus 1, okay? So I'm going to run that. And then I do a bunch of acrobatics over here to find the amplification factor. And oh, it's going to fail, of course. Let me kill the kernel. Sorry. Okay, let's try again. Okay, so you do this, and this is your modified equation. You have your advection term, your diffusion term, and your dispersion term, okay? And you can choose how many terms you want to pick. So let's say you want to get to the 4th order diffusion. You just change the order over here. Say I want, not 35, just 5 terms, let's say, okay? So we run it again. Look at that, okay? So 4th order diffusion, 5th order dispersion. This term, yeah, this term is multiplying the 5th order dispersion. You can collect and simplify even further, okay? But this is so cool because now you just automate the process. Let's say I want to do the Lax, let's say, Lax Friedrichs or Lax Wendroff, let's say. Okay, I hope this works. All right, let's see if this works. And let's do 3 terms. So what this is doing, it's just automating the process of finding the amplification factor. Look at that, okay? Advection and then the dispersion term. Okay, it's pretty cool.